probably saw it up in the sky. They are visible with the naked eye. The seventh and the eighth planet are not so simple. Uranus, for example, can be barely seen with the naked eye. If you go into a very dark place and you stare at the sky for a very long time, you might be able to spot it. Neptune is totally invisible to your eye. Let me start with a little bit of the history of what we know about our solar system. Like I said, the first six have been known for a long time. The seventh one, Uranus, this one was discovered, the first planet to be discovered using a telescope. A telescope that was maybe this big, fits on the size of your desk. We now know that it orbits around the Sun at an average distance of about 19 astronomical units. 1 astronomical unit is the average distance between the Sun and the Earth. The eighth one, Neptune, this has a very interesting story. This planet was actually predicted to exist before it was discovered. After Uranus' discovery, physicists, astronomers were putting Newton's law of gravity to the test. They try to make predictions, very precise predictions of Uranus, where Uranus would be on the sky, and they try to compare that with the actual observations. And they found that it did not exactly match where Uranus was supposed to be, according to Newtonian gravity. Half the people said, oh, Isaac Newton is wrong. Half the people said, well, maybe there's something out there. It took some time, but it was actually finally predicted through lots of hard work that one night Neptune will appear in this part of the sky, and so astronomers should go and look at that spot. And lo and behold, within 1 degree, which is about the size of your fingertips, at the distance of your arm, it was found within 1 degree. Now, Neptune is what we consider the outermost planet in our solar system. It orbits around the Sun at an average distance of about 30 astronomical units. Now, I have to say something about Pluto, since Pluto was once a planet. When I was in elementary school, I did learn that Pluto was, in fact, the 9th planet. But in 2006, it was demoted down to what we now know a dwarf planet. It's not quite the planet, but maybe close enough. Now, the person who demoted Pluto, his name is Mike Brown, professor at Caltech. He is not very popular because, for obvious reasons, but he and his colleague at Caltech, Konstantin Batygin and Mike Brown, predicted that there might actually be a true giant 9th planet in the outskirts of our solar system. Now, how do you look for things in our solar system? Well, if you look at the sky, and if you take a telescope and measure, say, a portion of the sky, a solar system object looks just like a star. It's a dot. The way to distinguish a solar system object from a star is through its motion. The Earth goes around the Sun once a year. The object is also moving around the Sun. So as the Earth goes around the Sun once a year, a solar system object would appear to wobble in the sky. So if you look at the actual motion of, say, Pluto over a 10-year period, it looks like this, that yellow coil that you see in the back. It takes exactly a year to complete one loop. It loops every year, but at the same time, Pluto is moving around the Sun, and so you have a combined motion of a circular motion and a drift in one direction. This is how you look for solar system objects. Now, let me tell you how Mike Brown and his colleague at Caltech predicted that there might actually be a 9th planet in our solar system. So these are the terrestrial planets, which includes our own Earth. Zoom out, those are our gas giants, Jupiter, Saturn, Uranus, and Neptune. Now, if you zoom out even more, there are a bunch of objects, but there are 6 in particular that go way out to the outskirts of the solar system, to about maybe 400, 500 times the astronomical unit. Now you look at this and say, whoa, okay, there are 6 of these things. Do you see a pattern? They're all pointed in this direction. Now, these were just random objects orbiting around the sun. You would expect these elliptical orbits to point in random directions. The random chance of this occurring, the fact that 6 are pointed in the same direction, and if you actually tilt this figure, they are actually orbiting close to a similar plane. And so Mike Brown and Constantine Keegan said, well, this is weird. You can't explain this. There's got to be something out there that is possibly shepherding the orbits into a particular direction. And after a lot of hard work, they came to the conclusion that yes, you can actually do this if there's in fact a giant planet, they call planet 9, with an orbit that is anti-aligned with the really extended orbit. So this is what we're trying to do at Penn. Penn is part of a large international collaboration. It's called the Dark Energy Survey. We built this camera and mounted on a telescope down in Chile. You see the big shiny dome behind me? That is the Blanco telescope, a 4-meter telescope down in Chile. We built a camera that's literally this big, as tall as me, weighs about a ton, and mounted on the top end of the telescope. What's special about this camera is that it's huge. In one shot, you can take a very nice, crisp, deep picture of the big part of the sky, which is not something that every telescope can do. Now, this camera was built for actually a different reason. As the name suggests, it's called the Dark Energy Survey. We built this camera to try to study the evolution of the universe. How did the universe begin? How is it expanding? What is the ultimate fate of the universe? That's what the other 200 astronomers in our collaboration are doing. But me and my colleague here, Professor Gary Bernstein, saw this and said, well, this is a very good camera which takes very good data. You can actually use the same data to find objects in our solar system. This is a picture, one exposure taken on our camera. You can see the size of the old camera in comparison, which can fit the full moon. We can fit many full moons in one shot. It's 500 million pixels, costs about $80 million. It's a very expensive instrument. We're taking pictures every night, and we're taking many, many pictures every night, and trying to look for things that move across the sky. Now, most of the objects are stars and galaxies. Stars move a little bit. Galaxies don't move at all. Solar system objects move quite a bit. I'm showing you here about 0.05% of the data that we have. Each star that appear and disappear are actual new things that we discovered in this particular part of the sky that were not present before. There's a lot of them. If you combine all of the data that we have tens of millions of new detections. Most of them are asteroids, main belt asteroids that orbit between around the sun, between Mars and Jupiter. But a small, tiny fraction of these are things in our solar system that are way out there. So we take these detections, millions of detections, and try to connect the dots. Because, like I said earlier, solar system objects move. They move in a very particular way, according to Newtonian gravity. So we take these detections, take many, many computers, and try to find the few objects that match up, that correspond to the same object in the outskirts of our solar system. So what happens is something like this. I'm not showing you all of the detections here. I'm only showing you the detections that correspond to actual solar system objects that are way out there beyond the orbit of Pluto. In this small area, you can see 3 camera pointings over here, which adds up to about 0.15% of our data. We found 15 objects. Now try doing that with a bunch of undergraduate students here. Students here are absolutely great, but if I tell them to do this manually, connect a million dots and try to find the ones that match up, you really need a computer. Now, I have to confess that despite all the hard work that we have done so far, we have not yet found Planet 9. I probably wouldn't be here if I had discovered it. But we did find at least one interesting object that is rare, and you look at this picture, it's insignificant. It's that little dot. Of course, it doesn't come with the arrow. It's that little dot that we discovered. It looks like nothing. But this turns out to be a distant dwarf planet that we discovered. It's just like Pluto. It's way out there. It's slightly smaller than Pluto. But this is the technology that we have. We can see these things out to very large distances. Now, we've done a lot of follow-up work on this and try to identify its nature. We now know that it has an orbit that looks like that in comparison to the orbit of Neptune. And you can see how the dots move across 3 different nights. Again, it's insignificant, but computers are able to detect this. Now, this name DD comes from distant dwarf. It's an acronym for distant dwarf, and we put in the vowels in between. We now know that it has a size of about 600 kilometers. It's a little bigger than Pennsylvania. This thing currently sits at 92 astronomical units. You have this ball of rock that is roughly as big as Pennsylvania, 92 astronomical units that we are capable of detecting it. In terms of its brightness, its current brightness, it's comparable to taking a candlestick and putting it at the distance of the moon, and we are able to detect that. Now, like I said, we haven't found Planet 9 yet. We have looked at about half of our data. We're actively sifting through the rest of the data that we have now. Does it exist? I don't know. But if it's in our images, we'll definitely find it. And like Stephen Hawking said, that we should all look up at the sky and not down to your feet. I'm trying to do that. I'm trying to look up at the stars with the hope of maybe sometime in the future finding this and understanding more about our solar system. Thanks for your time.